Hello physics students, welcome back. So we spent some time now talking about objects that move in circular paths, and we've talked about what's special about that kind of motion, in particular that it's motion with constant acceleration, because even if objects don't change speed, what they do is change direction at a constant rate. And for objects that accelerate at constant rates, that means there's a constant net force. Now, for an object that moves in a circle, that net force we define to be, the requirement is that that net force is always towards the center of the circular path. And I'll just say, as a refresher, here's a circular path. What we talked about is that at any instant an object, say, might be moving that way. Here's the net force on that object. This is a right angle. And what that means is this net force has no component this way, no component that way, so can't speed the object up by pushing in the direction of motion, can't slow the object down by pushing opposite the direction of motion, but does push, right? There is a force, but that force can't change the object's speed, but the object has to accelerate, so that means the object has to change direction, because velocity includes not only how fast something goes, but what direction it goes. All right, so then we said this direction inward is called the centripetal direction. And for any object that moves in a circular path, net force is inward, or what we call the centripetal direction. Okay, so we've talked about primarily things that move in horizontal circles, which is to say that if you trace the path that an object follows, that path is a circle that lies in a horizontal plane, like parallel to the floor. All right, but now we're going to talk about objects that move in paths that are circles, or maybe parts of circles, but that lie in the vertical plane. All right, so this might be the bottom of a valley, and here's an object down here in the bottom of the valley. So if this object's in the bottom of a valley, or this is a bowl or something, that's a marble rolling around the bottom of a bowl, that's at least part of a circular path. Even if it's not a complete circle that an object moves in, that section of a circular path is still part of a circle and still follows the same rules for circular motion. So there's one case we'll look at, and in that case, well, we might as well dive in. This object experiences a force due to Earth's gravitational field. And, okay, that force is, say, that big. Well, if this object is going to be moving, now if it's not moving, if this object's simply sitting there, then the force exerted by the bowl on the object, don't draw this, is that big, right? For an object that's, just because there's a bowl there, if this thing does not move, then sure, it's in equilibrium. Those two forces are equal in magnitude. All right, but if this object is moving, and I'll say that it's moving this way, that's not a force. I'm not trying to represent that as a force. I'm just telling you the object is in motion. Well, now there's a normal force exerted on this object that is bigger than mg. All right, here, n has to be bigger than mg, and the reason is because for an object that moves in a circle, the net force must be inward. All right, the only way for this object to experience an inward acceleration is if there's that net force that's inward, and so the force exerted by the bowl has to be bigger than the gravitational force. Okay, if we take that same object and now let it go over the top of this hill, well, it still weighs what it weighs. But now as it goes over the top of this hill, again, the net force must be inward. So the force that the track, or whatever you want to call this, the hill, exerts on the object has to be less than mg. That's not an n. N has to be less than mg. And why is that? Well, same reason, because the net force has to be inward. This object is accelerating. That acceleration is towards the center. That means the net force is towards the center. Okay, so we're going to get into a bunch of situations where, I mean, the convenient thing about the place we're talking about, the places we're talking about, top or bottom of these things, is that mg happens to point, notice, directly away from the center, directly towards the center. So that's why these places are convenient ones to talk about. Okay, because as you'll see in a few minutes, when we write net force statements, that mg can go directly into our net force in the centripetal direction statement. So I'll run you through a few examples. The classic one, here's that right where we were, top of the hill. All right, so here's an object moving, let's say this way, over the top of the hill. It doesn't matter if it's right or left, but it's moving. Just want to be sure about that. Well, there is a force, mg. There is a force, n. And in general, for sure, n has to be less than mg to make the net force inward. And if we're going to write a net force statement in the centripetal direction, remember, inward is positive, outward is negative, so that means that mg minus n equals mac. All right, the definition of the positive centripetal direction is inward. And so, I mean, the one further step we could do here is say that mac is mv squared over r because a is v squared over r. Okay, and here we get to some neat kinds of situations. All right, in our classes we've talked about apparent weight, or what you feel like you weigh. You'll notice that it's possible, even without, well, the feeling of weight, you feel like you weigh what you do because of the force that maybe like a seat in a car exerts on your butt. So if that seat does not push on you, you feel like you're weightless. All right, so when we say what you feel like you weigh, that's all about what the normal force is. And in this case, if you feel weightless, well, what that means is n equals 0. And check it out. If we made this normal force nothing, well, this object still has a force, mg, that points towards the center of its circular path. mg all by itself provides centripetal force. We'd say mg is mac. And then we could say, well, your centripetal acceleration must be g. And if you want, we could go further and say g is v squared over r, and we could solve for v or solve for r, or find what you want to find. The greater point being, we can talk about some special situations and what you feel like and how that relates to the normal force. Notice, we're taking this general net force statement, applying the fact that for a special situation, really at a special combination of v and r, normal force can be 0. There could be a situation where you feel like you weigh half your weight, right? We can start with our generic, for this situation, statement, right? If we feel like we weigh half our weight, that means the normal force is half of your weight. And well, we got a common factor of m in every term there. We get g minus a half of g. Well, that's a half of g is ac, or a half of g is v squared over r, and you have solved for what you want to solve for. Okay, so look for these feels like. That's entirely connected to, at least in this case, normal force. Okay? Okay. Here's a different one. Inside this loop, let's see. Well, there's two places that we'll talk about. All right, one of them is here at the top. All right, at the top, let's do this. I'll make a little delineation between at the top and at the bottom. Here we are at the top. This object weighs what it weighs, mg. All right, at the top, this object's in contact with that track, the loop, and so there's a normal force exerted by the track on the object arbitrarily that big, also down. All right, so when we write our net FC, we've got mg plus n is mac. We want to go farther, we say mg plus n is mv squared over r. They're both explicitly positive because both of those forces, when we're at the top of this track, point inward. Inward's the positive direction. All right. Again, we could, or a rider in this situation, in a moving, driving in a car around a vertical loop, in a roller coaster car around a vertical loop, could feel weightless. That implies n equals 0. Right. So we take this expression and say n equals 0. All right. So sure, if we got rid of that normal force, mg would still point inward. This thing can still move in a circle, even without, for an instant, being in contact with that surface at all. All right, and like it was before, this says that g is v squared over r. Solve for what you want to solve for. All right, feels like you weigh half your weight. That means that the normal force exerted on you is half your weight. So we would say mg plus half of mg equals mv squared over r. Right? I'm starting here, substituting in what n feels like. All right, we've got a common factor of m everywhere. We've got g plus a half of g. That's 3g over 2 is v squared over r. Solve for what you want to solve for. Feels like you weigh 3 times your weight. Are these getting redundant yet? Okay, that means n is 3 mg, right? mg plus 3 mg equals v squared over r. We've got a common factor of m in every term. So that's 4g is v squared over r. Do what you want. Okay? Fair enough? Okay. Now, at the bottom, here's our rider, our object. Still weighs what it weighs. mg is the same as it was anywhere. But now normal force, okay, normal force has to point inward because it's the force that the surface exerts on the object. That force always points perpendicular to the surface. And I know that n has to be bigger than mg because we need a net force inward. All right, in general, we'll start by saying the inward minus the outward. There's our net force statement. Now, some specifics. Feels like you weigh, feels like you're weightless. N equals 0. Well, this can't happen. If n was 0, the only force acting on this object would be mg pointing outward. That doesn't make this object accelerate towards the center. Therefore, it doesn't move in a circular path. This is impossible. At the bottom, n must be bigger than mg. This is also impossible. You can't feel like you weigh anything less than your weight. That would make the n half as big as mg. The net force would be outward. Also impossible. It should make sense to you based on experience, perhaps if you've ridden in a car even at the bottom of a little dip, or if you've ridden a roller coaster at the bottom of a little hill where you start to go back up. You don't feel lighter than what you normally weigh. You feel a little heavier for an instant as you get to the bottom of that circle and start going back up. What is possible is that n could be 3 times as big as mg. That would give us a net force inward. All right, so n minus mg, we're saying 3mg minus mg is mv squared over r. We have our common factor of m in every term. Now we get 2g is v squared over r. So notice it's pretty neat. It's possible to feel like you weigh 3 times what you do in 2 different places on this track, but the speed would be quite different. All right, this speed solves to v is the square root of 4gr. I'll just write it, 4gr. You could take the 4 out and make that 2 square root of gr. Right, and then this v down here would be the square root of 2gr, and those are different by a factor of the square root of 2. All right, so it is possible to get the same experience of feeling heavier in 2 different places, but at 2 different speeds. Okay, moral of the story here is, as long as you can start here and write the correct net force statements, and guess what? They come from the correct drawing of a free body diagram. Then we can apply some special situations of what things feel like, and what that means in this case is what the normal force is, or how that normal force relates to mg. Here's another one. Yeah, sure. You're swinging on a rope. It's a pendulum sort of thing. All right, so let's see. The place we're talking about is at the bottom. At the bottom, we could have mg like that. And tension must be bigger than mg. And it must be because the net force acting on this object must be towards the center. All right, so here at the bottom, T has to be bigger than mg. In general, well, our net FC says T minus mg is mv squared over r. Right, the inward explicitly is positive, the outward's negative. And here's our MAC. You notice I stopped writing MAC and started just using the fact that AC is v squared over r. Now, could you feel weightless at the bottom? No, you cannot. If you're swinging on a rope, scratch that. If you're hanging on a rope, not moving at all, there's a tension force like this, there's mg like that, and the fact that that rope pulls upward on you with the force of your weight means you feel every bit of your weight, because that's how much that's how much kind of muscle strength you have to use to hold yourself up. Well, if you move at all, the rope pulls up harder than your weight, and it would be harder for you to swing at the bottom. You'd have to use some extra muscle strength to hold up or to exert that that extra force on the rope that the rope exerts on you. So impossible to feel weightless, impossible to feel anything less than your weight, but it is possible to feel heavier than your weight. Right? In this case, what we feel like is not a normal force, but that, in this case, is what the tension force is. So our T minus mg is mv squared over r can turn into 2 times your weight. Common factor of m. And this is g is v squared over r. Sure, solve for what you want to solve for. Okay? What we didn't do is we didn't do the case where here's the object at the top of here's the pendulum at the top of the path, and that's being pulled by the rope downward. All right, that would be exactly like this, except the force downward isn't a normal force, it's a tension force. Okay? So, there are several situations where the common types of questions are, hey, at the top of the path, you know, what forces act on the object? And, you know, in a certain funky kind of perfect speed and radius combination, maybe you feel like this or feel like that. But solving those problems all comes from being able to draw the right free body diagram, write the correct net force statement, and maybe apply the special feels like situation. Okay? The most important thing here to be able to do after drawing a good free body diagram is just remember that positive is inward, negative for the centripetal direction. Positive is in, negative is out. So when you're writing your net force statements, that is the must. Okay? Farewell.